Okay, so I've added a couple extra variables here to our sort of typical approach. And we have 3 models, each one with an additional exponentiated variable. So let's take a look at what happens. Summary m.1. So we have our first one. This is the one that we're kind of most used to seeing. You have your x variable, the coefficient, and this actually has an r squared of 0.29. And as I add more of these guys in, let's kind of just focus on the r squared here. It's actually increasing 0.2957. And then the next one, 0.3606. Okay, so this is another indication. This is not entirely the main point here, but actually another indication, right, that the r squared isn't a necessarily great indicator for the quality of the model, because we know this should be just based off of the x1 and not x2 and x3 as well. But in this case, right, your r squareds are increasing. So let me actually kind of take this to the extreme. And I'm going to extend this so that I have something like 50 exponentiated versions of x. So it'll be x. So y, instead of just being a function of x, it'll be a function of x plus x squared plus x cubed, and so on through x to the 50th power. Okay. So that's what this thing is doing. If you want to kind of follow along, right, we have a for loop that goes from 1 to 50. I've initialized the data table, and then I'm going to hold x to the 50 or x to the n, and then bind that into the table so that I will have essentially sort of 50 columns of this table, each one having x, x squared, x cubed, and so on and so forth. So that's how I'm doing it in this kind of for loop here. We'll do that. So now if I take a look at this table called example, we'll see, like I was mentioning, some 50 columns like so. Okay. So now I can if you remember from the end of class last time, we talked about having this sort of training set and then having this testing set, right? So the whole idea here is that you have some data upon which you are able to train your model, and then some data which you would use to test the model. And so normally there's some nuances of how you go about getting a test set, but in this case, since it's a totally artificial data set, I can just make up the test set myself based off of how I know I created the initial training set before. So here I'm going to make this test set. And I'm going to do the same thing so that I can populate the test set with all of the x's that I needed to make my model. So the x all the way through x to the 50th. Okay, so I've created two functions here. So the first one here is called return prediction. So given a set of explanatory variables, this is going to return the prediction on new data from predict table. And then it's going to give you the mean squared error of the training and the testing sets. All right. So we'll do that. And this is just a way essentially of compiling the results. Okay. Uh-oh. Predict table not found. That is okay, one sec. Predict table. Okay, here. Okay, I think it's because I called that something different, which is test. So, okay, so let's do this. Predict.table is test. I think that'll work now. Hopefully. Uh-oh. See, I make mistakes too. Is it because I included the y in here? Okay, so let me walk through what I'm attempting to do here, and maybe I can figure out what I'm doing wrong. So here, I am regressing my model across all sort of 50. So actually, so you can do it this way, which I've written. So on line 51, the reason why you have line 51, right, is that normally when I write out the LM function, you have to do y tilde x plus x1 plus x2 plus x3. And I don't want to have to sort of write them all out manually. So you can use this function here as formula and then put in all of the input variables. And then treat that as the formula that goes into your LM. So that should have everything in here. Okay, so in my output, I have predict. So this is, I take the model that I initially ran on the training data set, and then I feed in the new values that I made in the test set as my new data. And that's going to give me a whole set of things that I can measure as an MSE test. So those would be all the predictions on the new data. And I can compare that to the mean squared error of the training set. Okay. So given all that, there appears to be some kind of error here. So let me see what's going on. predict.table. So let's take a look at test. So we should have 100 and then x1 through x50, which is what we have here. And let me see if this works. Oops, sorry, one sec. Wrong one. I'm going to take a look at what gets passed into here. Same type of thing. Great. So there's an alternative to doing this formula thing. We can do this. So as a shortcut in the LM, instead of doing this formula, you can put a dot like this. And what this approach does actually is it just says take all the other variables besides y in the data that's getting passed into LM and run a regression on that. So let me see if this works. Oops. Oh no. Y equals predictions. All right, sorry for this. I'm going to find some old code here. Sorry about this. 8. It's still doing that thing. Okay. All right. Data equals test. All right, sorry about this. Troubleshooting in the middle of class is not ideal. Let's see if I can find all.return, return prediction. 1, 2, 3. Okay. Okay, I think I found the issue. Okay, got it, sorry. Okay, so let me just take a look. Yeah. Traceback was me. Yeah, so okay, this is a like handy tool for folks. If you are working with these like large functions, and you're running it and you're running into like errors, traceback will tell you essentially like where the error is coming from. Okay, so sorry, I did something really dumb. I basically had copied and pasted code and I didn't execute something earlier, which is why it was not working. So sorry, I'm I'm having like a full-blown panic attack in the middle of a class here. Okay, so the point of all of this is, let me make this thing here, okay, and we can zoom in. All right, so, okay, again, you don't need to have followed along. All of this code is going to get posted. So essentially what I've done is I've run 50 regressions, okay? That's what all this code is doing. And these are what the regressions look like. It's the exact same data between X and Y. You know, it's actually the same thing that we've been running with the random points here. And one of the things you can do that's sort of commonly done is we can increase the explanatory power of the sort of X variables by including exponentiated versions, right? Because that includes anything that might be linear, anything that might be quadratic, anything that might be cubed, and so on and so forth. And so all of those coefficients are going to have some kind of values, and then it's going to cause the line essentially to start wiggling closer and closer to your points, okay? And we can see that happening here. So in the first one where it's just X, it's a straight line. In the next one, it's X plus X squared. You get this line, X plus X squared plus X cubed, right? And so the more explanatory variables that you have, the more sort of ways you can capture the sort of degrees of freedom within your X's. And we can start to see the line sort of getting more and more complicated. We'll learn about this a little bit later, but one of the sort of features of having lots of powers is really sort of at the ends, the line starts to get really crazy. So you do see some things like this happening. But this harkens back to the very first day, or not the first day, but the first day we started talking about the more theoretical stuff past the R tutorials. Remember, I drew that plot about matching up all the lines, right? And there's this concept that, okay, we might be running into issues like overfitting, right? If I have a line that goes through every single point, you guys all said, well, that model is probably not very good. And the reason why it's not very good is because if I were to, for example, take a different set of points that belonged in the same family, a test set, and then I were to throw those points into here, right? You could imagine that now the regression does really poorly because that squiggling line was overfit to my training data. So we can see that happening in a more quantitative way right here. So this should have, yes, okay. Okay, I didn't print it onto here, but the other thing is if you look at the R squared, right? As your line squiggles more, it's getting closer to your points, and it's essentially capturing more of the variation. So this is going to be the lowest R squared. This is going to be the highest R squared. But again, that doesn't mean that this one is the best model. And one of the ways that we can do this is by looking at the mean squared error. So the mean squared error, right, tells you essentially the average distance between my line and my points. It's this, you add up all your residuals and you basically square them, take the average, right? So in the top left corner, this is the mean squared error of all of the points in this model. And what you can see is as I add more, squiggliness into the model, your mean squared error decreases because my line is getting closer and closer to all of my points. And you would expect that, right? Because if it were, let's say you did x and x squared, and if it were like all just in the x, at the very least, your coefficient for x squared could always be 0, right? So as you add more variables, it's always going to decrease the mean squared error because it always has, at the worst, an option of just setting that equal to 0 and having it equal to, y equals beta x. Okay, so both in the R squared and in the mean squared error, we can see improvement across all of these models. And this should be, yeah, this is going to be your lowest mean squared error. But what happens if we take our test set? So this is stuff that the model didn't train on, and we take our models and we run it against the test set and check the mean squared error. That's this value here, okay? And what do we see happening in this case? We actually see that the mean squared error increases as I'm adding more variables. Okay. So going back to the original model, which is just we know as being y equals beta x, right? That's how we created the y's. Look, and if we choose the mean squared error, the out of sample mean squared error, the one that's run on the test set, that's actually going to tell us that the best model is actually the first one, right? Because when you add in all these other points from your test set, they're all overfit and your mean squared error is actually increasing. And so if we were to go by the out of sample mean squared error metric, it's going to tell us the best model, and And in this case, it's actually the correct model, and we know it to be the correct model. Okay, great. Yes.
Is there any difference with mean squared error and like the reason behind going with mean squared error instead of the RSC residual standard error?
Yeah, so they will probably be pretty close substitutes most of the time. I'm trying to remember the equation for residual standard error. It might have to do with computational complexity, although they're probably going to be pretty similar. I think it's more kind of just like a standard. That's what people have been using. But if you were to do residual standard error instead of a mean squared error, I think your results will generally be pretty similar. I'm kind of rolling through all of the cases in which we're going to be using sort of mean squared error as a metric. And yeah, I can't envision one being sort of particularly nuanced where you'd want to use that instead of the residual squared error. So yeah, I'll double check that, but I think that you should typically end up getting pretty similar results with an RSE. But you know, when you look in all the textbooks and all of that, yeah, you'll usually find that the MSE is a pretty standard metric for doing this. I guess they got to pick something, right?
Yeah.
Okay, so any questions or confusions about this? This is kind of a concept that we're going to be working with for a lot of the rest of the class. So make sure that you guys understand this. And if not, let me know.
One thing that I thought it was interesting is that after like 14 or 15,
yes,
it's not changing much. Like mean squared error on the top left.
Yeah. So it's like 95.14 for quite a while.
Yeah, and the shape also isn't changing much.
Yeah. So think about it this way. Each sort of marginal additional explanatory variable that you're adding, it has to contribute to capturing the variation in the data beyond what's already been captured. And so, you know, these variables are inherently constrained in some way because the way that, you know, the squiggliness works based on the power, a lot of that variation will already have been captured with previous variables. So it should be expected actually that each subsequent decrease here will capture generally a little bit less of the variation, and hence your MSE should be decreasing, or yes, should be decreasing by a smaller and smaller amount as you sort of progress, generally. Yeah. Did some, yes. Okay. So all I'm doing is I make up an X and a Y. We'll do it like this. So I've totally made up a random X and Y, right? So A, B, C, D, E. And then I use these values to define my Y, and I use these also to do my X squared, X cubed, X fourth, and so on. Okay. So this would be my training data. And then I run a regression of my Y on this training data. Data equals training. And then I measure the MSE for this. And then totally separate, I make a new testing data set. Okay, so I have X and Y here, and these are going to be totally different. So E, F, G, H. So this is going to be my model. And these will have totally different values from here, right? Because I've generated these as like in a separate process randomly. So all I'm going to do is I'm going to take this model and I'm going to feed in this testing data. And then I'm going to measure. So this is MSE train. I'm going to measure a new mean squared error. And then I'm going to compare these. That's what's happening here. Okay. And this concept of trying to do this out of sample testing is going to be critical for us to address this overfitting issue, right? We can see the power of it here where it's like, oh, actually everything past the first one is overfitting. That's the concept that we want to be able to apply to a bunch of these other modeling approaches. Okay, so let's go to our notes. Stop sharing. All right. So kind of to reiterate here, got my X and my Y. And then if I have some data points, right, I can do something like this, or as I was just kind of showing, I can have some kind of crazier line that captures all of that variation. But if I were to, if this only represented part of the data set, right, and I had other points in the data set, like so, you can see that suddenly this second prediction line is doing really poorly because now, like, let's say my distances are like way farther away compared to the distance they would be with just the straight line. Okay. So that's the concept that we were just kind of exploring. And so I want to talk about this in a slightly more fundamental way here. So as I add more variables, I am able to capture a certain aspect of the model in terms of sort of reducing the variation in my error. But essentially what you're doing is known as a bias variance trade-off. Okay, so maybe some of you guys have seen this type of thing before. We'll have a sort of bullseye thing like this. So you can have low bias, let's say high bias, and then low variance and high variance. Okay, so essentially what you're aiming for is this guy right here. You want a low bias, low variance. So in your bullseye, you end up making some kind of predictions where everything is kind of sort of centered correctly. If you have still low bias but high variance, you might have something that looks like this. So you're still centered, but things are kind of spread out. And so we'll think about what this sort of analogy means in our data analysis. You could have low variance but high bias. Looks something like this, right? You can cluster really closely, but you might be off from what you wanted. And then the worst, right, is if you have both high variance and high bias. So you might see something like this. Okay. So your clustering isn't very good and you're sort of off center. All right. So formally speaking, we can do this mathematically. The error is the expectation of my y minus your predicted function here. These are just your residuals. And mathematically, okay, so if folks have done this in statistics, it'll look something like this. You don't need to memorize this, but I'm making this form for a particular reason in just a sec. Let's see. Okay, so you can take this and kind of simplify it into this form here. Again, don't worry about this. The reason why I'm sort of drawing this out, because each of these things actually represents something in sort of a traditional statistics term, and it ends up looking something like this. Qualitatively, we can describe this as bias squared plus variance plus noise. Okay. So the error that you have in your model sort of relates in this sort of way is described essentially by these two terms plus some random stuff that you can never really control, okay? And what's particularly interesting about this is that this has universally a particular type of pattern. Okay, so going back to that example of the x squared, x cubed, all the way to x to the 50th power, as we add more variables, you are increasing the complexity of the model. This is what this means, okay? So generically, you might think of model complexity as basically, in a simple way, as adding more explanatory variables. As you add more explanatory variables, you will find that your bias will decrease with model complexity. So this will look something like this. The offset of your points in the data compared to your model line decreases like such. However, the variance will increase in this sort of way. Okay, and so here you have a total error term that looks something like this. So this is my total error. You can kind of think of this as the error of the test set data points that you're putting in, and this as the error of the original training set points. Okay, so total error, right, is variance plus bias. And so really what you want is this sweet spot here. And the way we get this traditionally is doing the minimum of your testing mean squared error. Okay. Any questions about this? So let me see. Last class, we talked about a sort of more generic way, a generic technique of doing this, right? This was the cross-validation that we ended on. And so what I would like to do now is give a more sort of systematic algorithm for how to do cross-validation, and then walk through some sort of custom code to make sure we really understand what's going on. A lot of times, I mean, cross-validation is such a prevalent sort of technique. A lot of times the functions that we'll be using will have them built in, but both so that you guys can have the ability to do it yourselves and so that you understand what's going on sort of behind the scenes, we're going to walk through kind of building our own cross-validation algorithm. All right. Actually, I'm going to do it on this side because we're going to lower the screen in a second. This way people can still see what the steps are. So a type of cross-validation known as k-fold validation. The steps are: 1, divide data into k subsets. Calibrate model. On all but one subset. Predict y hat on the subset of data left out. Left out of calibration. Then we calculate MSE based on out of sample prediction. And then repeat process, leaving out different subsets each time. Until all k subsets are done. Okay, so build our data, basically make an assignment. Let's say you want to do a 5-fold cross-validation. Each row will get assigned like 1 through 5 number. Take out, let's say 1, calibrate the model on 2 through 4 or 2 through 5. Do a prediction of the model that you just ran against what you left out, and then calculate the mean squared error there. And then repeat this process, now leaving out 2, then leaving out 3, and then 4 and 5, and then you can do like an average of the MSE to get at your model's ability to do your sort of model's out of sample average mean squared error. Okay. So let's build this. We'll move this back down, turn this on, share the screen. Okay. So k-fold cross-validation. So this is going to be some kind of function. What do you guys think I should put here for my k-fold? If we're thinking about generically sort of operationalizing this into a function. What would be my inputs? Yes. Yes, the data. Perfect. Okay, so that's one. We're going to just call that input. And there's one other thing that I would want to put in here. So if we look at this sort of algorithm, what would I do related to dividing the data up? Yes, exactly. So I'm going to call that number of folds. Okay. So step number one is that I want to, it's kind of like what I was describing. Let's say I want k equals 5, and then I have my x and my y. Okay, A, B, C, D, so on and so forth. Essentially, the next step that I want to do here, the way that I do this thing is that I'm going to add a new column. And here, I just want to do randomly 1 through 5 and assign it to each thing. So this is kind of my index column. Okay. So it'll be random 1, 3, 4, 1, 2, 5, 3, 2, 1, so on, right? Just a randomly generated index column. So let's make that column. I'm going to first make a vector called index. And that is just going to be random numbers from 1 to the number of folds, right? That's my k. And you're pulling these numbers out of the hat. The hat contains numbers 1 through 5 or numbers 1 through fold. And the number of times that I pull out of the hat is equal to what? What do you guys think? What was that? So the actual number of folds it would be in this case 5, right? But I'm not just drawing 5 times. You're drawing equal to the number of rows in the data that you're putting in. Okay, so that would be n row input. And we'll be drawing with replacement, right? Because there's only 5 numbers and you have to draw more than 5, so replace equals true. And we're going to take our data and we're just going to add a new column, this thing, and that column will be this index vector that we just created. I am going to do a little trick here where I'm going to start with an empty vector and fill it up later. So I'm initializing this thing here. Okay, and I am now going to try and do this procedure, but I'm going to loop it because I want to repeat. So in number 5, I'm going to repeat this process a certain number of times. Okay, so for n in, okay, how many times am I going to repeat this? Number of folds, exactly. Right, so we're going to do this procedure k times. And so k is our number of folds. So we're going to do this for loop like this. Okay, and I now want to take this data set, okay, and I want to separate it so that I have my training set and testing set. So here we'll have training, and this will be omitting, let's say we want to omit all the ones. So this will be x, y, k, and now let's say B, C, not D, right? E, F, whatever. And the indexes here are going to be 3, 4, 2, 5, and so on and so forth. And then we're going to have a testing set, which is going to be all the ones that have a 1. So A, okay, something like this, D, and so on and so forth. So the way that I can take this, our original data set, and separate it is like this. Training data, I'm going to make this, and that's going to be from my original inputs. And all I have to do is say input dollar index does not equal to n. Okay, so if we are on k equals 1 in our for loop, it will make a training data set by grabbing the original one and omitting everything where the index is not equal to 1. And you can imagine the testing data set is pretty straightforward here. This is exactly the same thing, but we want to grab everything in the original data where the index is equal to, in this case, 1. Okay, so our model will look generically like so. Okay, I'm actually going to leave this part out for a second. We'll come back to this. So we have our model, which is run against the training data. And then we have our predictions. So that would be you predict on the model hold, and then we input the new data here. So new data equals testing data. And then we can do the mean squared errors. Mean squared error dot hold is mean of testing data and our output. So, okay. You can make this kind of generic. In this case, the thing that I'm going to actually run against is I'm going to do this against our data set from last time on wages. So let me go back here. And I'll put in one of the equations. So maybe something like earnings against, let's do height, sex, race, education. But again, you can actually customize your function to be sort of generic and not sort of specific to a single model. If you put like the variables that you want to describe as your y's and your x's like as an input into the function, but we won't do that for now. This is a little more straightforward, I think. Okay, so our mean squared error. What is our mean squared error? It is your model prediction minus the points. So you get your residuals, you square all of them, and then you take the mean. So this is our actual points, our actual y, which is testing from the testing data set. It's the earnings minus our predictions that we made in line 106. So we're doing step 4 now. And line 106 is step 3. Line 107 is step 4. We will square this, and then you do the mean. So that will give you the MSE. And then I am going to go back to my original trick here. I was mentioning I have this MSE.all in line 101. which is going to store each of my mean squared errors progressively. So that looks something like this. So just to be clear, this is a little programming hack. So you can have a final vector, and then you have some kind of for loop with a value that gets held, and then final gets appended onto this. So here, this would be an empty value. Okay, so let me see, final for loop number. So in the first loop, this is just empty. And then let's say hold is, generated by other data, and this ends up being A. So final will then be so your final will take that A and store it. So in the next loop at the beginning of it, it will be A. And then in the next loop, it'll be A, B. And then in the next loop, it'll be A, B, C. So we're doing this kind of trick to store the value of each of the MSEs as we walk through the function. And that's it. MSE.all. Okay, so if let me grab the wages data set really quick. And let me make sure I'm in the right spot. Nope, okay. One sec. Set my directory. Okay, so I am going to wages. Fread wages.csv. Okay. So let's see if this function works. Okay, fold CV1, and I'm going to input my wages data, and then let's do a 5-fold validation. Please work. Okay, sweet. Okay. So these are my mean squared errors across across the different sort of folds. And you should see generally there's going to be some variation, but fairly consistent, right? And you might get some kind of outliers sometimes because the points that you randomly happen to sort of move in your test and training set, might be slightly different. Okay. So again, the mean squared errors are going to be sort of a unique value to the problem that you are looking at. But so unlike your R squared value, which is always between 0 and 1, But these values can be compared when you're looking at sort of the same sets of models with similar response variables. So if your y's are like the same, that can be a point of direct comparison. So in this case, what I'm going to do is I'm going to just straight up copy and paste my function that I made, this k-fold CV1. And oops, did I do it too many times? Okay, I'm going to make this into k-fold CV2, and all I'm going to do is I'm going to change the equation. I'm going to take out height, and I'm going to put in age. So this is a way with these two different k-fold tests that I can compare the out of sample mean squared error between two different models. Okay. And let's see what happens. So I can take the mean of my k-fold CV1 of wages with 5, and I can compare that against the mean of k-fold CV2 with the same thing. So all I'm doing here is I want to compare two models, right? One is height versus sex, or sorry, wages / earnings is a function of height, sex, race, and education versus earnings as a function of age, sex, race, and education. So age and height are swapped out. And when we talk about sort of model comparison, you know, we talk about all these diagnostics, you know, R-squared, standard errors, and so on and so forth. At the end of the day, I kind of consider this to be the gold standard, right, for model comparison, because at the end of the day, this is telling us which model does a better job at predicting out of sample. And that's what these numbers are going to represent when I run this model. Okay. So in this case, you basically say, okay, I have these two models, they train on some data, and then external data, I run it, and this one with the age variable is going to do a better job at predicting the outcome of earnings compared to my previous one, because my MSEs, the sort of mean squared errors of your out of sample tests are better. Okay. Any questions about this? It's a lot to digest. I'll have these notes online, so make sure you go through them and kind of understand what's going on here. Yeah.
So when we create like MSC page, we are taking the mean of tests.
Yeah. Yeah. So because why not the training one? That goes back to that bias variance chart. Okay. Let's do this real quick. Okay, we'll have some data that looks like this. And then let's say I have a separate data set that's testing. These are maybe the points that I might have omitted. And we can do we can do this guy, and we can do this guy. Okay. So so for the black points only, okay. So this would be our training set. Is which one has the lower MSE, the blue line or the purple line? Black points only. The purple line. Okay. So purple line. So MSE will be smaller than, right? And you want the, we always want the, okay. So training set. So this would be red points. Which one has the smaller MSE? It's the other way, right? So MSE is less than the purple one. Okay, so forget all the math and stuff. Like which one do you want? So like if, sorry. So if you were looking at this chart and you wanted a model to predict some kind of outcome, would you rather have the purple line or the blue line? The blue line. And that's because we suspect that the purple line is like overfitting, right? And you can see that the size of the errors are probably going to be larger, you know, especially if I do something like this, right? Because that distance is bigger than this distance. That distance is bigger than that distance. So we want, what we want is the mean squared error of the things that you aren't trained on, so that we know you're not overfitting. Because with this one, right, you can overfit as much as you want. You can have x to the 50th power, right, and get closer and closer to those points, but you will have issues of overfitting. So that's why we want only the testing set MSE and not the training set MSE. Make sense? So that's what's happening here in this function. We're looking at the testing set MSE of these two formulas to determine which one's better, right? So the next topic that we're going to be talking about is known as model selection. I mentioned this at the end of our class in the last class. This is where maybe I have a giant table of a whole bunch of explanatory variables. Maybe you have x1 through x50. And now I want to figure out a strategic way of determining which variables to include in my model. Okay. And you can run the model many times. And you need some kind of metric to figure out, should I do x1 through x20? You know, should I just do x3, 5, 8, whatever, right? So this is what we're trying to do with model selection, figuring out what variables go into the model. And we're going to use this kind of thought process to determine and compare different combinations of variables. They're not always going to use this k-fold validation. there are some kind of standard metrics that people use to prevent overfitting. Okay, and we're going to look at sort of different ways across some of these selection methods to prevent overfitting. But principally, they're all trying to do the same thing, which is kind of like this. Okay. Again, we're going to be doing basically this for the rest of class. So if anyone has any questions or confusions, let me know now, or you can ask me later. That's fine too. But try to make sure that you have this principle fairly squared away. Okay.
I have a question.
Yes.
I was wondering the value of k, how many folds?
Yep. Yep.
That's like, does it come from experience, or is there a method to find out?
Yeah, there isn't a generic rule for that. I almost always just do like 5 or 7, but the sort of statistically robust way you would want to do this, right, is you could test across a number, like a couple different number of folds, and make sure you're getting consistent results. That is to say, like if you're comparing 2 models and you do a 3-fold validation, that, you know, okay, let's say model 1 is better than model 2, and then you do a 5-fold, and then it's model 1 is still better than model 2, and then you do a 10-fold, model 1 is still better than model 2. You wanna make sure that there's consistency there. Practically speaking, what you're doing, right, is you're taking your data and you're dividing it up. You wanna ensure that in your training set, like you have a reasonable amount of data that you're still kind of working with, which is why, like, you wouldn't do, like, let's say you had 1,000 rows, like it wouldn't really, well, actually that's not quite true. I was gonna say you could leave one out at a time. That's actually a thing. It's called leave one out sampling. So you could go all the way to like 1,000-fold if you wanted to, but sometimes you'll start running into like computational limits when you do stuff like that. So there are some practical things to consider when you're doing these sorts of tests. But yeah, honestly, when I do it, I usually just do like 5 or 7. Okay. Model selection. This is the task of selecting a statistical model from a set of candidate models. All right, so suppose we have some data. Y, x1, x2, x3, all the way ... to xn. So which model is best? Is it y equals beta 1 x1? Or is it y equals beta 2 x2? Or y equals beta 3 x3? And so on and so forth to all the combinations. is that y equals beta 1 x1 plus beta 2 x2 plus, right? We got a whole bunch of different possible sort of models that we can test. And so you can imagine that the number of combinations increases sort of very quickly. Don't quote me on this. I think, or let me see if this is in my notes. Yeah. Okay. So if you have n variables, number of combinations will scale to something along the lines of 2 to the n. So this rapidly increases exponentially. So we need some kind of efficient method of kind of filtering through these. This oftentimes is, people approach this as kind of like more of an art, in the sense that like, oh, I have some suspicion that, you know, these variables are correlated with y, so I'm going to run my regression on that. And that makes sense to do oftentimes, but also can lead to biases. You might, because of your initial thought process, you might exclude certain variables that might be important. So I want to introduce kind of more systematic ways of doing this, and simplifying this process where you don't necessarily have to look through all of these combinations, that may avoid some of the pitfalls of doing it kind of by intuition, which isn't to say that you should totally ignore intuition. That can be sort of an important part of this as well. And you can kind of try and fold some of that together. Okay. So I'm going to talk about a couple metrics besides the mean squared error that we can do, or that are commonly used. And what I'll say about these is that sort of despite sort of common practice in using some of these other metrics, I will mention that this k-fold validation can be applied to any of the techniques that we're going to be talking about. And so just keep in mind that in addition to some of these metrics, the mean squared error, the out of sample mean squared error, is always an option that is available to you to measure. Okay, so alternative criteria. Criteria for model selection. We've got the Akeki, I don't know if that's actually how you pronounce it, information criteria. I don't know if that's how you actually pronounce it, because no one calls it that. It's always called the AIC. So this is an estimator of the relative quality of statistical model. And here, smaller is better. Okay, so the smaller your AIC, the sort of quote unquote better the model is. So AIC looks something like this. So 2K minus 2 ln. So this is number of parameters And this is known as the maximum likelihood value. Okay. You don't need to know too much about this, but what I'll mention is that, so the maximum likelihood value, this is kind of a measure of how good the model is, essentially. And what you'll notice is that you're subtracting this, so the larger your likelihood value is, so the sort of better your model is, the smaller your AIC will be. But there's a penalty function here. And this is the thing that deals with overfitting, right? Adding more and more variables will make this better, but at a trade-off, because now you're penalizing your AIC by having a larger and larger positive value. So in the same way that we think about leveraging like the MSE out of sample thing to kind of find the right model, right? This is inherently doing our bias variance trade-off, right? Because this term will be trying to reduce bias, this term will be trying to reduce variance, and that's the sort of AIC. Okay. Another common one is known as Mallow's CP. So this will reduce the RSS while taking into account the number of parameters. And this is actually equivalent to AIC for linear models. The equation looks something like this. CP is equal to 1 over n of your RSS. So the RSS is the residual sum of squares. Sum of squares plus 2k sigma squared. So this is number of predictors. And this is our estimate of variance. Yes. Okay. Yeah. Sorry. Yes. I'll do that. Yeah. I think it's all visible on YouTube, so you can. Yeah. I'll also. So actually. Also, I should say, I don't know if people are using this, but I post PDF notes of all of this material in Canvas as well. So that will be sort of written there. Okay, but so Mallow's CP reduced the RSS while taking into account the number of parameters, equivalent to AIC for linear models. So this equation has the RSS on the left plus 2 times k times sigma hat squared. So that k is your number of predictors. This is our estimate of variance. So you are multiplying these two things together so you can get kind of the lowest point in both, right? Because as your predictors go up, this will go down, right? And as this goes You still want some aspects of the model to capture the bias parts. So you're reducing your residual residual sum of squares. So another common version here. Okay. We'll quickly cover two more. We have Bayesian information criteria. So similar to AIC, but with difference penalty. For parameters. Okay, so BIC is equal to ln natural log n times k minus 2 ln my maximum likelihood. So this is better if smaller and bigger penalty for models with more variables. Okay, so you can see this portion is the same as my AIC, but my number of parameters, a penalty is different. It's ln n, number of data points times the parameter, number of parameters. And so this part most often will have sort of a larger penalty as you have more variables compared to the AIC, which means in your model selection algorithms, if you choose to use BIC versus AIC, you likely sometimes will come up with different outcomes. It might say this model is better than another model differently. Okay. Last one is the adjusted R squared. So 1 minus RSS over TSS. This is the same thing. This as calculating the regular R squared, but now there's a modifier term n minus 1 over n minus k minus 1. So this term RSS TSS, this is the same thing as how we calculate our R squared, but now we've introduced this extra term here, n minus 1 divided by n minus k minus 1. And what this will do is introduce a slight penalty for adding more variables. Okay, so that again, penalty essentially to help try and prevent overfitting. Same principle in all of these guys. You can see consistently we've got K here, K here, K here, K here. These are all to address this principle, right, of preventing overfitting. Okay, so some differences. So I'm just gonna, I guess, talk about these. But as I mentioned, the sort of more detailed version of this will be in the notes. So thinking about the R squared versus the AIC, BIC, or Mallows, the R squared is more kind of trying to do how well does the model that you're running explain the observed data. Whereas AIC, mallows, and BIC are all going to be trying to do something slightly different. There will be explaining how well the model fits new data. And typically, again, lower values for AIC, CP, and BIC means that you typically can expect better prediction the lower value each of these things are. Okay. All of these will penalize having more parameters. The R squared is definitely more popular than a lot of these other metrics, but arguably sort of not as strenuous statistically in thinking about this particular issue. AIC and CP versus the BIC. Typically, we argue that the BIC helps to better identify the true model, the larger your sample size is. So as n approaches infinity, BIC will sort of empirically do better than the AIC. But if you have a small data set, AIC tends to minimize the possibility that you are selecting a bad model. So, okay, generically speaking, BIC for larger data sets, AIC for smaller data sets. And as I was mentioning before, all of these are alternatives to the out of sample mean squared error, which you should always be able to do for any of the algorithms and techniques for model selection that we'll be talking about. Okay. I think that will be a good stopping point for today. Yes, we definitely don't have time to get into our actual algorithms. So we'll kick off with that next time. And we'll be leveraging these guys. Again, this concept of bias variance trade-off, cross-validation, we're going to be doing this a lot. So please make sure you understand this. Take a look at the notes that I post. Yep, and I will see you guys all next week.